The experiment is my personal favorite research method to use, in part because it determines cause and effect. And I'll show you how it does that. But first, let's talk about how you conduct an experiment. You begin with a theory, and that could be about just about anything. The field of psychology is pretty wide. It may be that you have an idea or a theory that caffeine ingestion speeds up reaction times. Or it may be that you have a theory or an idea that exposure to violent role models increases aggression in children. Or you may work for a pharmaceutical company and you're trying to find a drug to improve memory. Drug is brand new, doesn't have a name, you're testing it, so you have a theory or idea that this new drug X improves memory. The next step is to form a hypothesis. Warning, this is a very important vocabulary term. I've written it in a bright gold. You should know it's important, it's underlined. Hypothesis. A hypothesis is defined as a simple testable statement. And formulating a hypothesis is absolutely necessary when you conduct an experiment. And here's how you formulate a hypothesis. Again, a hypothesis is a simple testable statement. And it's a statement about causes and effects. And it should take this form. If something, then something. The portion of the hypothesis at the beginning, if something, is the cause, and the end of the statement is the effect, then something. So my hypothesis might be, if people ingest caffeine, then their reaction times will be speeded up. Ingestion of caffeine is the cause, and the change in reaction time is the effect. Or you may hypothesize that when children are exposed to violent role models, they begin to behave aggressively themselves. And my hypothesis becomes, if children are exposed to violent role models, then they will behave aggressively. Again, we are identifying potential causes and effects. If people ingest drug X, then their memories will be improved. Again, a simple testable statement about cause and effect, or the expected causes and effects. This leads us to two very important vocabulary terms: independent variable, dependent variable. The if part of the hypothesis is associated with the independent variable, which is actually manipulated by the experimenter, by the researcher. The dependent variable is the then part of the hypothesis, the result, or the expected result. If people ingest drug X, then their memory is improved. The independent variable is ingestion of drug X. That is what is being literally manipulated by the experimenter. They're giving people the drug. The dependent variable would be the effect on memory, and that's the effect in the hypothesis. If people ingest caffeine, then their reaction time is speeded up. What's the independent variable? It would be ingestion of caffeine. If people ingest caffeine, then something happens. What is the dependent variable? That is the change in reaction time, or the expected effect. If children are exposed to violent role models, then they behave aggressively. What is my independent variable? What is my dependent variable? The independent variable is manipulated by the experimenter. That experimenter is showing children violent role models, and that is causal. So exposure to violent role models would be my independent variable. What is my dependent variable in this situation? We expect the children to behave more aggressively. That's the effect, that's the then part of the hypothesis, and that is the dependent variable. Again, a hypothesis is a simple testable statement in the form of if something, then something. The if part is the independent variable, causal. The then part is the dependent variable, the effect. And in this class, you'll need to be able to formulate a hypothesis and identify independent and dependent variables. Our goal is to disprove the null hypothesis, which states that the independent variable does not influence the dependent variable. In fact, we would have to accept the null hypothesis unless we can provide evidence to the contrary. That is the default. Unless we can show that manipulation of the independent variable affected the dependent variable, we have to accept the null hypothesis. And as you might imagine, that is not the favorite outcome when you're conducting an experiment. As we're talking about how to conduct an experiment, we have to consider operational definitions of our variables. We need to operationally define our terms. What do we mean by ingestion of caffeine? What do we mean by reaction time? We need to be more specific. This is important because we're going to eventually publish the research findings, and other researchers are going to read about our results, and they're going to attempt at least to replicate our study and extend it further, answer more questions. And if there's a problem with that, it can be very damaging to reputations. If, for instance, I conduct an experiment about the effects of caffeine and I fail to operationally define my terms, then someone else reading the study could try to conduct the study again with different participants in a different location, and if they do not get the same results, then that certainly could hurt me as a scientist. So I need to operationally define what I mean by the independent variable and what specifically I mean by the dependent variable. Taking the example of ingestion of caffeine affecting reaction time, what dosage of caffeine and how is it administered? I could either give someone a caffeine pill or I could give them a cup of coffee. And personally, I think the caffeine pill is better, basically because I can control it better. And I'm not the best coffee maker, but even besides that, I would not be able to accurately control the dosage of caffeine in a cup of coffee. So a caffeine pill is probably the better idea here. I also need to operationally define what I mean by reaction time. And if you think about it, there are many ways to measure reaction time. I could use a driver simulation test and assess reaction time that way. But maybe a simpler way for some preliminary research would be just to write a computer program so that people could come to my office one by one, sit at my computer. Back in the old days, this was possible. And basically take a reaction time test. When the word go appears on the screen, then the person would hit the space bar on my computer keyboard as quickly as they could. And so over 100 trials per participant, where at random intervals the word go appears and they have to react to it, I would be able to assess reaction time. If I am conducting the research with children, again, I need to operationally define my terms. What do I mean with the independent variable? What do I mean with the dependent variable? So I am manipulating exposure to violent role models in this study. That's my independent variable, exposure to violent role models. How do I do that? Specifically, I need to be able to describe it, publish the procedure very clearly so other people can come along and replicate my work. There are numerous ways to do this. What I might do is hire some actors and have them behave aggressively in front of children. Perhaps not the best technique because it's very difficult for an actor to behave exactly the same way in front of each child or in front of each group of children. So I would probably want to use a video or a film of someone behaving aggressively. I could just take a 10-minute clip of a film that contains some violence. I always ask students to tell me what movies they watch that have violence in them. One example that often comes up is the film Pulp Fiction, which is pretty violent. I could take 10 minutes of that film, show it to children, presuming I go through an ethical review board to do this, which we'll talk about later, and then put them in a situation where they can behave aggressively. So here, my exposure to violent role models, the independent variable, would involve showing children a 10-minute clip of the film Pulp Fiction. And I can describe that as I write a journal article very easily. On the other hand, maybe I decide I don't want to use a film like that. Instead, I'm going to use a cartoon. I'll show 10 minutes of some sort of violent cartoon. Examples that come up always include Tom and Jerry, which I think is an incredibly violent cartoon, and I've disliked it ever since I was a child. But there you go. That's a violent cartoon. So I show 10 minutes of Tom and Jerry, and I can easily describe how I expose children to violent role models. I can operationally define my independent variable. Now let's consider the dependent variable. That too needs an operational definition. And I want you to imagine that if I ask everybody in the class to participate as a researcher with me on an experiment like this, ultimately you would be going to a playground perhaps and watching children interact with each other, and you would be recording whether or not they behave aggressively or not. But we would have to decide in advance what is aggressive behavior. We're not all going to agree at first. Usually I ask people to raise their hand in class, if they think that one child hitting another child is aggression, and would you write that down as aggressive behavior in this research study? People always say yes. I ask then if you think that a student pushing another person is aggressive, and most people do say yes. I ask if name calling is aggression. Maybe one child calls another a poopy head. Is that aggression? And we have to decide in advance, is name calling of that type aggressive? What about if one child sticks her or his tongue out at another, makes faces? Is that aggression? We have to decide this in advance. We have to operationally define what we mean by aggression, and then we need to be able to report it as we publish a journal article for other people to read. All right, let's imagine that we really are going to conduct this caffeine experiment. And so I ask students to come to my office one at a time. I give you a caffeine pill, and then you sit at my computer and you watch the screen until the word go appears, and then you hit the space bar as quickly as you can to measure your reaction time. And every student has 100 trials. That means that I could find the overall mean for the group, and I would know a little something about whether caffeine does affect reaction time. And I'm hoping you realize that something very important has been left out here. There's the question of, well, what would your reaction time have been if you did not ingest caffeine? That's the beauty of an experiment. You make comparisons. So what I really want to do is have half of you come in and you ingest caffeine, and the other comes in and they do not ingest caffeine. That means I can actually make the comparison. I can compare what your baseline reaction time is without caffeine, and I can see if it's higher for the group who did ingest caffeine. This leads us to two very important vocabulary terms: experimental group and control group. The experimental group receives the experimental manipulation, and here it's ingestion of caffeine. So I'm testing the effects of caffeine, I'm conducting an experiment on that, and my experimental group takes the caffeine. In contrast, my control group is providing a baseline, a comparison. They do not ingest caffeine. Now suppose I actually do conduct this experiment with the experimental group and control group as I've described, and I do see a difference between the two groups in their reaction time. How do we know that it's because the experimental group ingested something? Doesn't have to be caffeine compared to the control group. So for that reason, we need placebo treatments in experiments. The control group needs to, in this experiment, ingest a substance that has no expectation of changing reaction time. And basically what you're trying to do is keep your treatment of the experimental group and control group as close as possible, as similar as possible. The only difference in the two groups should be whether or not caffeine was ingested, not whether or not something was ingested. So here what we would do is use a placebo. Many people think of placebos as sugar pills, and here it could be. And the experimental group takes caffeine and the control group takes the placebo pill. Now if I see a difference between the two groups in their reaction times, then I am pretty sure that it is the result of caffeine ingestion and not something else, some uncontrolled variable. Think back to our experiment regarding drug X and whether it improves memory. How do I design that study using an experiment? I divide participants into an experimental group and a control group. The experimental group receives drug X, the control group receives a placebo, and then I can test both groups for their memories and see if there's a change in memory that is the result of ingesting drug X. What about our experiment with young children? wondering whether exposure to violent role models increases aggression in children. Well, I would conduct it in a similar fashion. I would divide the children into two groups. The experimental group is shown that 10 minutes of Tom and Jerry, that violent cartoon, and then I would have a control group. And to be honest, they need a placebo treatment. Placebo treatments are not always sugar pills. So what I would do is I would select a cartoon that has no violence. In the past, students have suggested cartoons like Dora the Explorer or SpongeBob, whatever his name is. And then I would show 10 minutes of that cartoon to the control group. That would be my placebo treatment. Experimental group sees a violent cartoon excerpt, and the control group sees an excerpt of a cartoon that is not violent. Placebo treatments and the use of control groups are very important when you conduct an experiment. And if you ever read a journal article in psychology, and you will actually, then look to see if there's a control group, if it's an experiment, and consider the nature of the placebo treatment and think about whether it actually allows the two groups, experimental and control, to be treated identically, with the one exception of whether or not the participants were exposed to the manipulation of the independent variable. When I was working as a graduate student in New York City, working toward the PhD, I needed to take research consulting positions to survive. And so one of those, as I've mentioned, was at the Vera Institute of Criminal Justice in the Brooklyn DA's office. And while I spent most of my time interviewing second felony offenders, they also gave me another assignment, which I enjoyed. I was asked to review the literature on the use of acupuncture for addiction. New topic for me. So basically, I just went to the psychological journals and read the papers in the area. And one thing I noticed, and I was not the first, was that they did not have placebo treatments for the control groups. Many of those studies at that time, we're talking a while back, long while back, many of those studies had an experimental group receiving an acupuncture treatment in the portion of the ear that is supposed to be associated with addiction. The control group did not undergo any kind of acupuncture treatment. So these were poorly designed studies. Later, studies began to be published with appropriate placebo treatments, basically having the experimental groups receive acupuncture treatment in what are called the addiction sites in the ear, the outer ear, and the control groups receiving acupuncture in other sites on the ear that are supposedly not related to addiction. I'm not necessarily a proponent of this. I'm not an expert in this. I'm just interested in the experimental design here and reminding you that for the rest of your lives, you are consumers of psychology. If you look at experiments conducted in the field, look for experimental groups and control groups and appropriate placebo treatments. Now, here's another issue that's important when you conduct an experiment. And that is that we need to somehow control for the characteristics of the participants in the experiment. This is going to seem a little far-fetched, but imagine that I conduct a really badly designed experiment. And what I do is I conduct that caffeine experiment. And I ask people to come to my office. I give them caffeine and I test the reaction time. Others in the control group are receiving an appropriate placebo treatment. But I don't think about it properly, and I decide that, well, it's just more convenient if I have everybody in my experimental group about 20 years of age and everybody in my control group is 65 years of age or older. Now, that's not very smart. Research shows that while we do not lose our cognitive abilities as a function of aging, unless there's some sort of physiological or medical problem, we do, however, start slowing down in our reaction times. So here I would see a difference, a significant difference between the two groups in their reaction times. My 20-year-old experimental group is way faster than my 65-year-old plus control group. And this is a badly designed experiment. What I probably should do in this situation is use random assignment of participants to groups. Randomly assign whether or not participants are in the experimental group or the control group. Here, it's only two possibilities, so I could literally flip a coin. Heads, you're in the experimental group. Tails, you're in the control group. And that way, I would minimize the potential effects of age or some other kind of uncontrolled variable on the results of my experiment. So I've described a badly designed experiment where age was not controlled, as I assigned participants to the experimental group and control group. There's actually a vocabulary term that you need to know that applies to age in this situation. It is a confounding variable. A confounding variable is an uncontrolled variable in an experiment which could be influencing the results and making it so you can't really trust the results of the experiment. There are different kinds of confounding variables. As you read journal articles, you're going to, maybe their drug studies, you're going to think about how long since each participant had a meal, whether or not they had any other kinds of medical conditions that would make it so that there are different drug effects. Just common sense things, really. And I find that Psych 113 students are actually very good at pointing out confounding variables, which is an important type of critical thinking. Consider this situation. Once again, I'm being a very bad experimenter. Imagine that I conduct this caffeine reaction time experiment, and again, I'm lazy or not the brightest banana in the bunch, and I decide to conduct my experiment so that I've got my experimental group being tested for reaction time in one room, and I have my control group being tested for reaction time in a different room. And it just so happens that the room temperature is different between the two rooms. Maybe my heating system isn't working properly in the building, and my control group is in a very, very cold room, while the experimental group is in a room that is of a normal room temperature. And it's so cold in that control group room that my participants decide to wear gloves or mittens in order to stay warm while they take my reaction time test. Now you can imagine that if someone is sitting at a computer with a mitten on their hand and trying to hit a key quickly, that it's going to affect their reaction time. So this is a confounding variable, an obvious but very important factor to consider. There are other types of confounding variables to consider as well. Subject expectancy is one, and this is why we use a placebo for the control group. Because if participants or subjects know they're getting a caffeine pill and you expect them to have a faster reaction time, then that can influence their behavior. There's strong evidence for placebo effects occurring in the psychological literature in a variety of situations. On the other hand, what about the possibility of the experimenter being biased? The experimenter expects to see a certain type of behavior, and that causes them to actually see it. We'll talk more about that. But first, let me tell you a story. Decades ago, a researcher named Rosenthal decided to conduct an experiment to investigate experimenter bias. And what he did was go to teachers in the school system, and he told them a lie. He deceived them. He told them that he had designed this new intelligence test and administered it to all the children that were coming into their classes in the fall, and that certain children, and he identified them by name, were going to blossom this year because they had scored very well on his intelligence test. So then he left the situation and came back at the end of the school year. And it turns out that those children really did blossom, that they had higher grades, they had better commentary about their social behavior, and they scored significantly higher in standardized tests of intelligence. Those children had been randomly selected, but the teachers expected certain types of behavior from these children, and as a result of experimenter bias or a comparable psychological phenomenon, they actually did see the expected behaviors. Think back to our experiment with children, exposing them to violent role models and then observing whether or not aggression increases. Suppose we did conduct that experiment, and as the experimenter, I know who is in the experimental group and who is in the control group while I'm watching the children and recording their behavior. Now, there are going to be some ambiguous types of behaviors, and so if I know who's in the experimental group and who's in the control group, I may not be consciously aware of it, but I might lean a little toward identifying certain types of behavior as being aggressive for the experimental group or non-aggressive for the control group. I'm seeing the children's behavior through the filter of my knowledge of who has been exposed to violent role models and who is not. Literally, what I would do to conduct this experiment is train a group of undergraduate researchers to go out in the field and record aggressive behavior in children, and they would not know who's in the experimental group or who's in the control group as they watch the children. In our drug study with drug X and memory, what I would do is I would not want the person who greets the participant coming in to be tested in reaction time to know which person is in the experimental group and which person is in the control group. We don't know how we influence other people with our own behavior. So I would actually, as the experimenter or the principal investigator, I would set it up so that there's a little container, a little jar or vial for each participant, and there would be a pill in it, and the placebo would be identical to the caffeine pill. And the person who interacts with the participants would just hand them the vial, not knowing whether it's a caffeine pill or a placebo. I would have careful records of that information as the person responsible for the study, but the person interacting with the participant would not have that information. This leads us to two more very important vocabulary terms: double-blind and single-blind. In a double-blind study, neither the researcher nor the participants know who's in the experimental group or who's in the control group. Again, in a double-blind study, neither the researcher nor the participant knows who's in the experimental group or who's in the control group. In contrast, a single-blind study involves the participants not knowing this information, but the researcher who's interacting with them does know. And if you had to guess which is the better procedure, which is more controlled, which is the better type of experiment, of course a double-blind procedure in which neither the researcher nor the participants know who's in the control group or the experimental group, of course that is the better procedure to use. You'll read psychological journal articles that involve single-blind studies, and sometimes it's justified, but really, whenever it's possible, experimenters should use double-blind procedures.